Thanks for coming, and I am aware that this is right before the lunch, so I'm trying not to starve you. I mean, Luna may be many things, but you cannot eat it yet. So if you're interested in fetching the slides for your computer, here's the link, here's the QR code. So very quickly, what I'm going to talk about, first, I am going to outline the problems in software development as we see them. And this is not going to be anything new or surprising, but still this provides us with a nice background for Luna. Next, I'm going to show you the visual-textual programming using Luna as the example. Next, we'll see a bit of a technical overview of Luna as the language, and then some of the lessons we learned while implementing Luna in Haskell. And lastly, I'm going to tell you about the state that the project is in currently. Okay, so let's dive right in. So as you know, we as the humanity are producing huge amounts of data, and the rate at which we are producing the data is constantly growing. I have attached this, this chart which shows the size of the data in zettabytes that we produce. And this looks like an exponential growth, right? So to back this intuition up, I have a fun yet not really scientific fact. So in years 2014 and 2015, we have produced more data than in all the previous years combined, right? So this is the exponentiality. And better still, in 2015, we were only able to process around 0.5% of the data. So that's a lot of unharvested potential for you. But this all leads to creation of lots of programs, lots of software. And what's worse, the software is becoming increasingly complex. This is something that we heard about in the fantastic keynote today. So this growing complexity is a problem as the programs are becoming harder to comprehend. And actually, I'll risk saying that right now, we have trouble understanding some of our creations. And if you want a simple example, look at the meltdown inspector bugs. We've got the processors which are insanely complex, and yet we were taking them 100% for granted, right? They just worked. And then they turned out to have a massive hole inside that's causing losses right now. So to help us deal with the complexity, we are using tools. But there's a problem. So the tools themselves are quite complex, and they require learning. They incur some cognitive cost. And when you're programming, there's yet another problem. So when looking at the code, it's really hard to tell apart the layers of abstraction. It's really hard to say what's the implementation detail and what's the actual merit of the business logic. So I think you can raise your hand if you have ever refactored your code to make it look nicer and ended up messing business logic. Great. Yeah, that's kind of my point. And to mitigate this a bit, we are drawing diagrams, but I don't know anyone who likes drawing diagrams, and this is a burden, and this is something that feels like it could be done by a compiler, maybe automated. Okay, the next problem is that the programmers in most of the industrial settings are serving as translators from the domain knowledge that the domain experts possess into the code, right? So the programmers wouldn't like to learn as much about the domain of the problem as they need to, and the domain experts wouldn't like to really learn programming if they don't have to. But we have this huge communication barrier, because when you think about the operation of a software venture, there's programmers speaking code. There's project people speaking the language of the product. There's business people speaking money. So they cannot really communicate easily, but it's even worse. Imagine two teams of programmers, and each is implementing a service. And one of the guys asks the other, hey, what does your service do? And the other is like, oh, sure, here, look at the code. Is it obvious? I mean, not really. You cannot really tell. There's no easy way of understanding the code just by looking at it. So what can we do to mitigate all those problems? Well, the answer would be Luna, or rather Visual-textual programming. And I think one remark is in order. I am not trying to sell you a silver bullet that will magically make all of your problems disappear. I would much rather talk about a proposed paradigm shift, right? We propose a different way of approaching software development. So right now, let's take a look at what Luna actually does. And we have prepared a demo that's pre-recorded because I don't feel confident doing live coding with the levels of stress I'm experiencing right now. So you're taking data from an endpoint. Then you are extracting the JSON from the response, parsing it into a nice data frame. This is our way of visualizing like multi-dimensional nested data. You're looking up some stuff. You're filtering the list. And this is one of our use cases. We are visualizing all the trams in Kraków live. So we just want to get the positions from the stream. And now we thought, OK, this functionality is complex enough. We just collapsed it into a single function. Now it's just this simple node. And we proceed with the processing to transform it into a form that our map visualizers accept. And if you look at it, we can visualize the data that flows through our system at each step. So we have this live insight into the data. We know what we are doing. But at the same time, it's not like working with, say, Jupyter Notebook when your visualizations actually get in the way of your code. We can do something on the side, not interrupting the main flow of data. So this is what the data flow graph is about. And we often get asked, what's the difference between this and, insert data flow language X. We try to be a truly general purpose language. And some data flow languages tend to be simply an overlay over a set of predefined components. So that's not it. That's a full programming language. OK. Now, just wait a few seconds until we are able to get the visualization. So those are all of the trams in Kraków. Just to make it look nicer, we will collapse it even further. And I will talk about this feature more because it's insanely cool. We should have put some music in the background.
Can you tell what the colors mean?
Yes, of course. I'm running into the future a bit, but the colors are the types. We color and code the types. Ta-dam! All of the trams in Kraków. And thank you. Actually, a guy who recorded that sits in the front row here, so he should get all the credit. So the thing I wanted to touch upon, reiterate, is that we provide adjustable layers of abstraction. And by that, I mean each node is composed of other nodes, apart from the primitive ones. So if you think something is complex enough, you can collapse it into a function and then just view it from the distance. So you abstract away all the implementation details, and they don't get in your way anymore. The communication is much easier. So that's the process of doing that. And you can enter it again to work on the implementation detail, then zoom out. But onto the coolest feature of Luna. Luna is visual-textual language. Right now, we were only focusing on the visual part. But hey, everything you do in the graph actually is reflected by code. You create a node, and the line gets created. But actually, it works the other way around. So if you type something, is reflected by the graph. So if you have attended yesterday's keynote, those two representations would be isomorphic. Okay, so what are the benefits of this approach? Well, first of all, you get something that I like to call manageable complexity. It's so much easier to write correct programs quickly when you actually can, view the abstraction on different levels and have the clear layers of abstraction. It's a more natural way of thinking about the program's processing data, so you end up writing more correct code more quickly. Then the next thing is that this pipeline is really how people tend to think about processing data, about data flowing through subsequent transformations. So this is what it should look like, at least in my opinion. And the communication barriers that we were talking about, they are pretty much gone. The products people can inspect the program at the very high level, using those very abstract operations to tell them more or less what the program does and focus on the business logic. And then you can have a programmer dive right into the implementation details and, for example, I don't know, tune an FFT using the textual layer, which should be better for that, right? So everyone can choose their own view of the system. Okay, so now on to the more technical side of the presentation. So first of all, the way we were designing this language was very particular because, well, the dual representation was one of the very first assumptions that we were making. So everything we do every feature we add needs to work good in text, but also needs to be nicely, we need to be able to visualize it nicely, and it needs to be intuitive to work with in the visual part of the system. And that means that we have certain requirements that when you're writing a purely textual language, you don't have. So this influences our textual design as well. So I often get asked, is Luna dynamic or is it compiled? Where this paradigm is inherently dynamic because you are writing the program as you are processing the data, as you are adding more nodes, you're effectively creating the program. So it is dynamic. Though we can use compilation to compile some commonly used parts, to cache things, and to generally optimize the performance. And yet with all the dynamic stuff going on, we are leveraging the benefits of the static typing because we want to be able to guide the users so that they cannot, do nonsensical operations. The types are there to help. So our type system, what is it like? I must say it's heavily influenced by the Haskell's type system, which we really like. But at the same time, we think that Haskell's type system lacks the user ergonomics. Some things are more tedious than they should be. And we really like the idea of objects. I'm not going to go as far as saying object-oriented programming, but objects are cool. But we also like algebraic data types. And if you don't know what those are, I'm going to show in the next slide. But we also think that you need to have the accessors like scope to their own class. And what I mean by that is on this slide. So here you have a simple implementation of a data type that has two constructors. And this is the algebraic data type I was talking about. And on the left, you have the implementation in Luna. On the right, you have the implementation in Haskell. So you can see that we do support like full parametric polymorphism, just like Haskell does. So the foo takes the parameter a, which can be anything. We do support multiple value constructors. So this is the sum type that Philip Weller was talking about yesterday. And we do support pattern matching because we think it's an awesome way of deconstructing our data. Yet, well, our ADTs have an object-y twist. So think about what you need to do in Haskell if you want to name the two fields in the records the same. And here I'm talking about vanilla Haskell because I was made aware of some recent additions to GHC that will allow you to do this to some extent. But in general, you would need to create a type class, right? How many of you actually know Haskell? Oh, cool. Awesome. So you're aware of this problem. Well, in Luna, it just works out of the box like it would in Scala or in Python. You just write the name field in both data types, and you can use it very intuitively. What's more, we support row polymorphism, which makes working with accessors really intuitive, despite the fancy name. So imagine a situation like this. We're creating 3 data types, and 2 first ones have the name property. The third one has the name method, but this shouldn't be any different, right? Now, we are defining a function which says, well, give me anything, and I will give you its name property. So this, this makes some assumptions about the x, right? So, well, let us create some variables of those types. I may or may not have been watching Friends at the time of creating this talk. Anyway, we can use getName property on each of the objects, right? So we are passing completely different types to this function, and yet it can somehow make sense of this. And remember, we are a statically typed language. So this phenomenon is the row polymorphism because the type of this function is actually this. And this is a pure scripty way of writing this that you may have seen on this conference. And in Luna, you'll never have to type it. I mean, part of it being visual means that we need to be kind of implicit and helpful about the types. So you don't need to know that it's this under the hood. You just can use it like you would in Ruby or Python. So now this tiny operator that I think deserved its own slide. So one remark, this dot is the Scala dot, the Java dot. It's the accessor dot. It's not the Haskell composition dot. But we have 2 flavors of the dot. One is with the spaces around it, which makes it behave like this. It just applies this function to everything it finds before the dot. But there's also this cramped version of dot that sticks the operands together, and it just applies the function, the accessor, the method, to the nearest operand it's stuck together with. So this sounds pretty simple, yet it allows us to write cool code like this in the example. I mean, you don't really need to use parentheses anymore. And it allows us to chain the calls in a very elegant way. I don't know if you like what you're seeing, but I bet you can actually tell what the code does, right? Even without really having any experience in Luna. So that's the very intuitive semantics of the dot. Right. So the next thing I would like to talk about is how we handle computational effects in Luna. Because, well, as we said, we are a functional language, right? So first of all, we really like laziness. We think it's cool. It allows you to write beautiful and elegant abstractions, just like, well, think laziness in Haskell. So, for example, the data types are lazy with respect to their fields. So if you see the foo data type here, it takes something that, well, it's an I/O action, but it will, in this line, it will not print anything because it's lazy, it's a thunk. Then, functions do not strictly evaluate their arguments. And by the way, in Luna, if is a function as anything else. So this means that in this example, if we were to have strict evaluation of function arguments, this would actually print both, right? Because it would look at its arguments. It has 3 arguments, the condition, the true branch, and the false branch, and it would evaluate all of those. That's not what we want, right? Since we are lazy, we're not doing anything unless explicitly asked for it. So this if basically works as you would expect. Yeah, so we're using the call by need mechanism, which can, well, save us some time in different situations. Well, but all that said, we do have a strict twist in our effect system. And this is partially due to the fact that the lines of code correspond to the nodes. And then there is actually some monadic magic going on under the hood. But a good intuition is that if you have a line of code, it will evaluate. Okay, so it will not get lost. And it's quite easy to actually force the evaluation of terms. So in Haskell, sometimes you need to do a little magic to do that. In Luna, this is intended to be really intuitive. And I'm going to show you some examples. Well, the lazy data type fields we mentioned. In the example here, we are wrapping the function reading from standard input in a just value. And it does nothing. Nothing is read. It's nothing. But then we are calling get to extract this value from just. And it needs to actually evaluate the read. So it will read twice, right? Just as you call it twice. Then the function arguments, we have the const function that will just return its first argument. And it will not print anything, right? If it was eager, it would print hello. But it's not. And to show you that this approach that we are taking is really intuitive, consider the implementation of the const function and the sec function. Everyone knows the sec function in Haskell? Yeah. So this const will just give you the first argument, completely ignoring the second, while sec will explicitly invoke the effects associated with the a value and then give you the second value. So something a little magic-y in Haskell. In Luna, that's quite simple. So this also means that we can distinguish between like pure mapping and effectful mapping. So think map and map M in Haskell. The first map will just give you a list of unevaluated actions, while the second one will actually force evaluation of each action and do pretty much what you would expect in such case, right? So actually print something. And if you look at our source code and see implementation of each and map, the difference is pretty much the same as the difference between const and sec. So this all revolves around the same idea. So I promised to tell you a bit about the lessons we learned while using Haskell for a quite big code base and quite a big project. I don't think I need to convince the audience here that Haskell is really awesome. So it's type safe, right? The compiler does a lot of work that you would, or normally in a dynamically typed language, or even in a more weakly typed language, you would need to write unit tests for, which nobody likes. So this spares you some work. It's really concise. It's really clean. It has this mathematical cleanness to it, which we really enjoy. And then you have this cool feature that pretty much, if you're doing refactoring in Haskell, you just change, for example, the function signature, and then fix compilation errors one by one. When you're done, you're done. Think about constantly grepping for stuff in JavaScript or in Python and ending up breaking production code either way. That's really cool. Well, but Haskell also has the dark side. So the said laziness of Haskell and the non-Turing machine model of evaluation, right? It's like Lambda calculus translated by the compiler to run on the Turing machine. It may be hard to look at the Haskell program and say, I know how fast this runs. Sometimes it's really unintuitive. And then Haskell programs may be hard to benchmark. Again, you need to make sure that everything you benchmark actually evaluates, because GHC is a aggressively optimizing compiler, and in general, it's keen to conclude that you don't need a value and just optimize it away. So to that extent, yes, you sometimes need to fight laziness, even when, I don't know, doing something like a debugging print in a pure function can be tricky. Yeah, so we are using GHC.js to compile some of our Haskell code into JS. So that can be tricky, mostly because the resulting JS code is quite large. I mean, think of encoding the Haskell runtime system in JS every time you compile the program. So that's quite large. Also, when we are building our considerably sized Haskell code base, it consumes a lot of resources and a lot of time. Especially if you're keen on using template Haskell, you get large compilation times and some surprises. Okay, so one educational example. And if you're an experienced Haskell programmer, this probably will be boring, but if you're just starting, then this may be an interesting code. So do you know what this code does? It's quite straightforward. We have this unsafe and impure operation that reads a file, arbitrarily named, and then returns the tail of this file. So all of the lines except the first ones. And we know that tail is a partial function, so it will fail if you fetch it if you provide it with an empty list, right? So, well, as we are good programmers and we are aware of that, we are constructing a function that will that will wrap this unsafe computation and basically, well, catch any exceptions. And if they occur, we just return unknown, right? 100% safe, awesome code, rest assured, nothing will happen. So we are using this to wrap the unsafe and pure computation. We are extracting its result, and we are trying to print it to the console. OK, question 1. What happens if the file does not exist? OK, anyone wants to answer? Well, actually, it will be OK, right? Because we are catching the exception. And the exception will be thrown by read file, catching any exceptions. Everything's fine. But what happens when the file exists but is empty? Well, exception, right? But one that is not caught but by catch any, crashing your code. And you may think, nah, that's trivial code, right? But this code, wrapped with some additional logic, was the code that I myself used to crash production. So yeah, I learned some Haskell. So why does it crash? Well, because the tail that's returned here, it doesn't actually explicitly throw an exception. It returns bottom. It returns undefined. So it just flows through the safe get and through the catch any, because it's like, nah, there's not an exception. And only when you try to actually access this value, it sees, whoa, it's undefined. OK, let's throw an error. So you can write this exact same program, maybe changing one character or 4 to make it work like you would expect. So first of all, you can return here using the $! Which is a strict version of application of the function, which will actually force the evaluation of the tail and will encounter the undefined then. But you can also use catch any deep, which will go through, like all your code and evaluate all the actions right to the bottom. And it, again, will encounter the bottom and report an error. OK, so let me just tell you, ending, what's the state of the project. We have just open sourced Luna. And you can check out github.com/Luna to see our GitHub organization. There's quite a few repositories, but you'll be safe in assuming that the ones prefixed with Luna something are the ones you need to take a look at. And we do welcome any contributions. So please take a look at the GitHub. There's some work that we are doing right now and that we will continue doing. First and foremost, work on performance. This is one of our main concerns, but also FFI. So we would like to bind different languages, and I think the roadmap is first we need to bind Haskell, then C, then Python, then JS. I think we were able to make first calls to Haskell like yesterday. We would like to make the type system more expressive. Because right now it's very user-friendly, but 100% implicit. We would like to allow you to have more control over your signatures, and we are working on a larger set of libraries, and this is where we are counting on community support in the first place. So I encourage you to get in touch with us, the aforementioned GitHub org, also our website, and the chat, which we are, it's pretty active. I mean, we do have a vibrant community, so you might want to check this out. For like larger questions, there's the Discuss, the forum, and I think I need to mention that we are hiring. We are looking for a project manager, for DevOps, and probably for a JS magician. So do reach out to us. We are happy to review any application, and we are based here in Krakow. So it's like walking distance from here. Yeah, thank you very much. Hope you liked it.
Thank you very much for the explanation. Now I know what we are talking about. We have plenty of time for questions, so please go ahead.
Ooh.
Thanks for the great introduction. Luna is really a technology that we should keep an eye on. I have a nasty question, and sorry for that.
Oh, no.
If I would like to put together an application that, if you say data flow and data flow processing, I would think about neural networks. I would like to train a neural network to do some crazy face recognition, for example. I would like to deploy it to the server with 4 GPUs for training and deploy it to the mobile phone on the end user, running the recognition evaluation part on the GPU subprocessor and the application. Can I write this whole system, for example, what I would do today with TensorFlow in Luna? And is it in the scope of Luna? And if it is, when we can accept such a full coverage?
Sure. This is actually a complex question because the answer is in few parts. So yes, I mean, the last question, yes, the goal of Luna is to be kind of like the language zero, so like the language for all of your programming needs, right? So yes, you should be able to do that in Luna if we are successful in doing what we do right now. Then binding to stuff like TensorFlow, this is why we do focus on providing FFI, because right now it would make little sense in rewriting neural network libraries in Luna. Although there's some community effort, I mean, guys are creating neural nets in Luna right now. But I mean, not TensorFlow scale, right? So expect the bindings really soon. And once we have the bindings to Haskell and to C, like the set of libraries that you will be able to use is huge, right? And then there will come Python, which will give you, pandas, NumPy, Keras, everything. So yes. Then about the deployment part, again, yes. I mean, part of my PhD is to turn Luna into this go-to platform for serverless computing. So in general, we aim to, we would like to be for this use case, to be this glue language that, you have several services scattered and deployed. And when you really would like to see how the data flows between them, that's Luna should be good for that.
I have two quick questions. You weren't specifying the type signatures in your code in Luna. Is it possible to add them?
There is an ongoing work on that. That's part of the making type system more expressive. I was trying to put it mildly.
And the other one, what's the runtime of Luna? Like, does it compile to Haskell eventually, and you like run it on a GAC
okay,
or like something
so
else?
we are reusing Haskell's runtime system, but we are not compiling to Haskell per se. We have our own compiler, but yes, we are reusing Haskell's runtime system.
Hi. Can you give me an idea of the error messages?
Error messages in Luna?
Yeah.
Oh, didn't I show that? OK, so are you interested in the visual part or the textual part?
Both.
Yes. Cool. So I'm going to start with the visual part. So the error is a node with like red crossing and with an error message displayed under the node. But more often than not, if you have an error in one node, it propagates to other nodes because they cannot make sense of a node that, of the data that flows through them, but is flawed. So it kind of nicely propagates on the graph, and like the nodes are like with this, thing. Yes. And the textual error message are think GHC error messages, but formatted nicely and striving for more user friendliness.
I actually had another question.
Cool.
How strongly is it tied to its to this IDE, this UI? I think it's running on Electron. When I tried it out, it was pretty sluggish. It was a bit.
So the front end is a Atom plugin, and there is some community effort to actually detach it from Atom. So I think you should follow the forum and the chat because there's some work around that. Right now it's tied pretty closely because, we needed to start with something, but we are working on decoupling it.
Does it make sense to at some point have something similar to IPython Notebook where you compile it, you draw all your graphs, and then you provide it in a readable form on a web page without needing to compile it on the fly when the user opens the web page?
It's just we have some JS on the front end. We compile Haskell to the JS, but at the end of the day, that's JS. So it's a matter of once we decouple it from Atom, we are pretty much free to put it anywhere we like.
Is it possible to use forgot?
Yes.
Recursion. Is it possible to use recursion, and how you visualize it?
Yes, it's definitely possible. It's part of the question that we got at the party yesterday. How do we visualize functions? Well, think of a node with, it's just like a function to which you don't provide arguments, right? So the node has its ports standing for its arguments. So if you don't actually attach anything to the port, you get a partial function, right? Partially applied function. So then this node is kind of like, you see that it being attached to the input expecting the function. So the recursion is something like that. Except for the node calling itself, it's implicit. You don't have the looping arrow if that's what you're talking about. No.
Yeah. And second question is it possible to reuse functions, and how they also visualized?
How do you
visualize? For example, when a function is used in several places.
Yes. So the function view, like when you enter a node representing a function, it's basically the same data flow that you would normally have with concrete values, except that the source of the data is some abstract port, and the output is another abstract port. So in that respect, visualizing functions is pretty much same as visualizing, actual code, if that's clear. Actually, if you want me to show you how Luna works in real life after the talk, you're welcome to come.
Okay, I've got a short question. Would it be possible to kind of play in a slow motion the data flow? I'm asking from the point of view of LabVIEW, which is a purely graphical programming language created by National Instruments. I spent 6 years working in it, and I think Luna is fantastic. And this is basically something that, if it works in future, it's going to basically kill LabVIEW, I think. But would it be possible to kind of play? Because what LabVIEW allows you to do is you can play in slow motion. You can see what data type, what's the values, and it's kind of like a debugging feature for them.
So first of all, yes, we do have the visualizations under the nodes. So well, we have some examples that if you attach a constant stream of values into a node and then display its visualization, you actually see it appearing on the graph. So that may be the inspection you're talking about.
Probably is.
Yeah, so that would be on our website. I think you can see a video showing you precisely that. I mean, visualizing.
Okay, just the last 2 questions, right?
Have you had any bugs from getting map and each mixed up, or does the compiler catch it?
Sorry?
Have you had any bugs from getting map and each mixed up, or does the type system catch that?
No bugs that I know of.
Or did they have different types?
Under the hood, yes. But I mean, I cannot think of a use case where I actually mixed up each and map.
Okay.
Okay, there was someone in the front.
Yeah, there was here. Oh. I mean, you can approach me offline.
I want to ask a question about the duality between the visual representation and the textual representation. Do you preserve the spatial properties of the call graph in the text version of the program?
Spatial of the text?
No, so when you are showing the example.
So you're talking about graph to text and from text.
Yeah, so if you ordered those nodes in some neat way, then looks nice, and then you switch to code, and then you will lose that nice ordering. Or
first thing, you don't ever switch to code. Those two just live alongside each other. So you never actually switch between the code view and the text view, because this is something that happens on the fly. And so to that extent, you never need to retrieve the visual part from the code, because it's just always there. But the second part of his answer would be we keep some metadata in order to preserve the layout of the nodes. But the third part would be we also have some efforts in order to lay out the nodes nicely if they